Imagine a fragment of ice and dust, launched from the outskirts of a distant planetary system, perhaps ejected by the gravitational pull of a newly formed giant planet, or disturbed by the passage of a nearby star. That fragment began a journey through the Milky Way, a silent voyage lasting millions or billions of years. Today, one such traveler has crossed our solar system. It is known as 3I Atlas, an interstellar visitor whose chemistry, behavior, and structure have become the focus of an intense scientific investigation. And thanks to the James Webb Space Telescope and the SPHEREx mission, we now have a clearer understanding of its story. This is a journey into the science behind that discovery. When 3I Atlas was identified, astronomers quickly recognized its hyperbolic trajectory, the unmistakable signature of an object born beyond the sun's gravitational influence. Its speed, close to 98 kilometers per second, confirmed that it had traveled through the galaxy long before entering our cosmic neighborhood. As it made its way around the sun and began its outbound trajectory, instruments on Earth and in space turned toward it, aiming to understand not only its orbit, but its composition and evolution. The first detailed spectroscopic measurements revealed something striking. The ratio of carbon dioxide, CO2, to water, H2O, in the coma of 3I Atlas was dramatically higher than in most known comets from the solar system. Similarly, the ratio of carbon monoxide, CO, to water also appeared elevated. Estimates indicated a CO2-H2O ratio of roughly 7.6 and a CO-H2O ratio of about 1.65, several times above the values typically observed. These results raised an important question. Was 3I Atlas formed in an exotic, chemically distinct environment, or had something altered the chemistry of its outer layers during its long interstellar voyage? To answer that, astronomers needed more than observations alone. The James Webb Space Telescope, equipped with its near-infrared spectrograph, NIR-SPEC, captured high-resolution spectral data of the gases surrounding the object. These observations revealed precise molecular signatures associated with CO2, CO, and water. The SPHEREx mission added complementary infrared mapping, helping to characterize broader features in the coma and identify potential organic compounds. Together, these datasets confirmed a critical detail. The unusual chemical ratios observed were coming primarily from the outermost layers of the object, the coma and the processed crust, rather than from the untouched interior. This distinction would become essential for interpreting its true nature. As laboratory simulations and theoretical models show, galactic cosmic rays, high-energy particles that fill the interstellar medium, can gradually transform the chemistry of icy bodies. Over millions or billions of years, cosmic rays can break molecular bonds, trigger oxidation reactions, form new molecules, including CO2, create a refractory, chemically altered crust. These processes can affect material up to 15-20 meters beneath the surface of an interstellar comet. If 3I Atlas spent vast periods drifting through interstellar space, this constant bombardment could have fundamentally changed the chemical balance of its exterior. This provides a natural explanation for the unusually high levels of CO2 observed. To verify these hypotheses, researchers reproduced interstellar-like conditions in laboratory settings. They bombarded mixtures of water ice, carbon monoxide, and organic molecules with energetic particles to simulate cosmic ray exposure. The results matched the JWST and SPHEREx findings. CO could be converted into CO2. Organic materials became increasingly complex and refractory. The outer layers lost their original water abundance. A crust with low thermal conductivity formed. Computational models reinforced these conclusions, showing how heat from the sun would interact with this altered layer during perihelion, releasing gases that reflect the processed chemistry rather than the pristine interior. The combined observations and models point to a coherent scenario. 3I Atlas has a processed outer crust, rich in CO2 and altered organics, perhaps 10-20 meters thick. Below that, a primitive nucleus remains intact, a remnant of its birth environment, shielded from cosmic rays by the overlying material. When sunlight reaches the object, this altered crust sublimates first, revealing a composition that appears unusual compared to solar system comets. Only if deeper layers are exposed will the truly pristine chemistry emerge. Thus, the properties observed so far do not necessarily contradict a cometary identity. They reflect the natural chemical evolution of an interstellar traveler. What 3I Atlas teaches us is that the surface chemistry of interstellar objects cannot be assumed to represent their original composition. Instead, these bodies act as natural laboratories, recording millions of years of cosmic ray processing. This insight reshapes how astronomers interpret interstellar visitors. It also guides future missions and observations, emphasizing the need to track changes over time and across wavelengths. Each interstellar object brings both its origin and its journey written into its structure. 3I Atlas continues its outbound path and will approach the orbit of Jupiter in March 2026. During this period, missions such as Juno, as well as ground-based and orbital observatories, may have opportunities to monitor additional emissions, including low-frequency radio signals. The James Webb Space Telescope may also observe the object again using its mid-infrared instrument, MIRI, offering new insight into its surface temperature, ice distribution, and organic compounds. Meanwhile, upcoming observatories like the Vera Rubin Observatory will help track its brightness and structural evolution with unprecedented temporal coverage. Each new observation will add another layer to the story of this fragmented messenger from another star. The story of 3I Atlas is one of transformation across cosmic time. Its unusual chemistry does not imply artificiality or anomaly. It reflects the effects of an environment harsh and vast, sculpted by radiation, cold, and isolation. Thanks to JWST SPHEREx laboratory experiments and detailed modeling, we now have a clearer picture, a processed surface enriched in CO2, overlaying a pristine core that preserves the chemical fingerprint of its primordial origins. 3I Atlas reminds us that every interstellar object carries not just the signature of its birthplace, but the imprint of the galaxy itself. By studying these visitors, we deepen our understanding of where planets form, how materials evolve, and how the universe shapes the countless worlds that move between the stars.